dictated by these two velocities along the horizontal and vertical direction, and therefore the trajectory will be something like this. When it reaches the floor, we are fine. And we indicate with the symbol LD the distance along the horizontal direction needed by this particle to reach the floor, and LD is the required minimum length of the sand trap. This is a simple physical problem. This is a simple study of the movement of a rigid body. The rigid body is a particle. We know the horizontal direction. We need to know the vertical direction. The vertical direction is that of a gravel particle which is immersed into water, subjected to gravity. And you know that this vertical direction can be computed with the Stokes formula. Stokes formula is very easy to prove. It's very easy because it's a simple physical problem. And in fact, we have here in my web page the derivation of the Stokes formula. Oops, sorry. Just 1 second. Let me expand it. Here it is. I think you already studied the Stokes formula, so I'm not interested in repeating this proof. It is not required, but what you need to know is the Stokes formula. And I kindly ask you, you have two options. Either you learn this proof or you learn by memory the Stokes formula, because I may ask you at the exam, especially if you look well prepared, to discuss this problem. And if you don't know Stokes formula, it's hard to discuss. So you can, as I said, you can decide. It's easy to look at this proof, and if you don't like to learn by memory, you can just elaborate the proof during the exam. This is appreciated. If you don't mind learning by memory, you can just learn by memory Stokes formula. It's also appreciated. It's up to you. It doesn't make a big difference to me. And what is important for us now to notice is that the velocity, which is called Ws along the vertical direction, depends on the diameter of the particle squared. Which means that, of course, if we want to minimize the diameter of the sand, velocity decreases. Depends on the specific weight of the particle, which is normally fixed, is about 2.6 kilogram per cubic meter. Depends on the specific weight of water, which is unfortunately fixed. And depends also on the viscosity of the fluid, which is water, and therefore it's fixed. The knee is fixed. Okay. Once that we know Ws, we can compute the time required by this red particle to travel the distance of h, in this case 50 centimeters. It's quite easy, as we know. Time, t, is equal to h divided Ws. And therefore, we can compute at the stage LD, because LD is equal to t, computed from here, times v. Yes. As you can see, the problem is quite simple. Remember that when we talk about hydraulic design, usually problems are not complicated from a conceptual point of view. And what is a bit complicated is maybe to remember the physical laws, and therefore in this case Stokes formula. But the problems are not so difficult. And nevertheless, the design is a bit tricky, it's not straightforward, because there is uncertainty. In every computation that we make, there is uncertainty, but in this case in particular, there is a relevant uncertainty. You understand why? We are talking about a particle, an ideal particle that travels from the free surface and without suffering any impact from turbulence, then goes down along the floor. But if you have also some turbulence, of course, it's not so easy, because the particle with turbulence can remain suspended. And therefore, of course, we make any possible effort to limit the velocity here in order to minimize turbulence, but you know, when you get some gravel already settled down in the sand trap and gravel trap, then you have some interaction between the flow and the floor of the trap, and also the section of the trap is reduced because there is some sediments that settle down and reduce the section. So there is a lot of uncertainty, and therefore what is really difficult is to figure out how to deal with this uncertainty, and to figure out what may happen. And I mentioned before, you have to try to predict what may happen in terms of overflow, what is the way that the flow will follow. Anytime that you deal with water, you have to avoid uncontrolled flows, and therefore you have to make an effort. It is very simple to predict where water flows. Water flows by looking for the quickest way to get at a lower elevation. So we say in Italian, l'acqua va in basso. Water goes down. It's very simple. But on the other hand, it becomes so complicated because you are in a natural environment, and then you put an infrastructure, and the infrastructure has to interact with the natural environment in a way that is difficult to predict. And this makes dealing with water very difficult. This is why Leonardo said, we are not sure that Leonardo said that, but Leonardo, there is a quote attributed to Leonardo which says, when you deal with water, you have to first use experience and then reasoning. Because you know, reasoning means theory. You don't have to use theory in a crude way. You have to integrate theory with your experience, and this makes dealing with water difficult. Okay, let me go back to the sketch. As I said, for the gravel trap, usually we don't make a specific design. We may repeat, if we wish, the same reasoning. But actually, what we do usually is to take an empirical approach, like, okay, let's say half of the length.
Yes, just 1 second of this formula you put there. T is h divided by ws. So h is the height of the channel, and ws is the weight.
No, ws is the velocity in the vertical direction. Okay. I think I didn't make any, no. I don't think I used ws with different meaning. It's clear to you? Okay, perfect. Now, let's look at what happens after the sand trap now. You have again a step, and this step may be protected by a grid, because you may still have some floating material that traveled through the gravel trap and sand trap. Floating material means like suspended vegetation, something that doesn't sink. And therefore, if you want to remove also this floating material, you may put a grid there. And the grid may be equipped with an automatic procedure for cleaning it. And then let's look at what happens downstream. Downstream, you have to take the water and bring it downstream. Not always, because sometimes there are hydropower plants which have a turbine directly located here and releasing water directly back into the river. Now we are checking the opportunity of making this kind of low-head hydropower plants which have a very limited impact because they can use like natural jumps into rivers, and even if you have a natural jump of a couple of meters or even 1 meter, if the river is very large, you can build a structure that allows you to withdraw the water before the jump, route the water through the turbine and releasing water downstream, just downstream the jump. And therefore the withdrawal of water is limited, as I mentioned on Monday, to a few meters, which is fine because in this way you minimize the impact. Still you have an impact because routing water through a turbine generates anyway an impact because you can catch fishes and turbine the fishes, and also there might be an impact because anyway when you release the water there is maybe a localized turbulence. The localized turbulence may be dangerous not only for erosion but also for the ecosystem. So anyway there is an impact. Also there is some noise because the turbine is noisy, and the noise is another kind of impact to the fishes, to the surrounding settlements, human settlement, etc. But still it's an attractive solution because you are not deprivating the riverbed of flow. In most of the cases, anyway, you need to bring water downstream. This is necessary when you need to use the water for irrigation, for civil use. You need, of course, to bring the water to the users. But even for hydropower production, very often, water is brought downstream in order to gain head difference in elevation, because you know that the produced energy is proportional to the head, to the jump, and therefore in order to increase this jump, water is brought downstream through typically pipes in order to keep the energy, and then it's routed downstream by placing the turbine to a lower elevation. So you can convey water downstream in two ways, through open channel flow or through pressure flow. Pressure flow means that you have to use a pipe. Of course, if you figure out what's going on, if you use an open channel, water cannot be in pressure, because water is in touch with the atmosphere, and therefore water is at its surface at the pressure of 1 atmosphere. Punct. If you put water into a pipe, water can be pressured, which means that if you punch the pipe, you have water coming down from the pipe in pressure, reaching what level? Reaching the level where this pressure is reduced by energy transformation, is reduced to the atmospheric level. So again, if the channel the flow is open, water is not under pressure. If you put it under a pipe, the water can go under pressure. What's the difference? The difference is that if you use channels, you cannot go very steep, because of course you need, if you go very steep, you have a sudden increase of water velocity, clearly, because you cannot increase water pressure, and therefore the energy is transformed into velocity. If you lower the elevation of water, it means that you are decreasing the potential energy, which is transformed into other forms of energy. It can be pressure or can be velocity. And therefore, if you cannot increase pressure, you lower the elevation because you make a steep channel, you have an increase of velocity. This is very intuitive. If you build a channel and you increase the slope, you have faster velocity. And increasing the velocity is a problem because it causes erosion, and it's a problem because it's a loss of energy. If you want to turbine water to produce hydropower, you have to keep the velocity of water low. Why is this? Because you know that the friction of water on the sides of the channel is proportional to the square of velocity. Friction is loss of energy. So if you increase the velocity, you lose energy. Therefore, if you use a channel, it means that it must be very mildly sloped. This is not always possible, because if you can go along the hill slopes with the channel in order to not to lose elevation, okay, this may be fine, but the hill slope may be unstable, so it's not always possible to keep the elevation with the channel, and therefore it's not possible, and typically it's not possible in mountain regions. If it's not possible, you use pipes. What is the problem of pipes? Because we could use pipes always. Pipes have first an advantage. The advantage is that they are not subjected to evaporation, and they are not subjected to infiltration. On the other hand, being the flow pressured, they are subjected to leakage. And leakage is always present. It's impossible to eliminate. When you have pressured water, you have leakages. And these leakages may be difficult to identify. You know that there is a leakage, but where is it? Because the pipe may be kilometers long, you have to locate where the pipe got damaged. And also, when you have pressured flow with a pressure that can reach like 10 atmospheres, and even more than 10 atmospheres, you understand that it's something that needs to be carefully designed, because it's potentially dangerous, and you need to spend a lot of money to build very strong pipes. And therefore you need to make a careful evaluation. In any case, not in any case, if you build pipes, there is also another situation that you have to absolutely avoid. You don't have to allow air entering in the pipe with water, because if you have bubbles into the pipes, then the pipes get rapidly damaged, because you can understand what is the situation. You have bubbles that originate with high water pressure, originate like very sudden and repeated, I don't know how to say in English, but like when you take a hammer and you bang, 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 bang. I hope it was clear. And with the bubbles, you may have what in Italian we call sbattimenti, which means that water goes back and forth along the walls of the pipe, and this rapidly causes damage to the pipe. So you have to absolutely avoid air. This is a golden rule. Okay, how to avoid the entrance of air into this pipe? You avoid it by designing what is called an upstream tank, which is designed in order to keep always, even in the worst situation, a safe level of water above the ceiling of the pipe. And what is the minimum submergence that you have to ensure to the ceiling of the pipe? There is an empirical rule which says that once the velocity of the pipe in the pipe is known, and let me see what is the symbol that I adopted here for the velocity of the pipe. So let's determine VA, max velocity into the pipe. Okay, so once that we know VA, the mean submergence should be 1.5 VA squared divided through G. And this is the mean submergence of the sealing of the pipe. Mean submergence sealing pipe. Of course, you have the water surface. The level of the water surface is regulated by the level in the sand trap and gravel trap. So in order to make sure that you have enough submergence, you need a tank to allow you to lower the level of the pipe to make sure that you have enough submergence. Now let me show you, I think I have a couple of pictures, just one second. I don't remember what they are. Give me 1 second, I try to. I would like to show you some pictures related to some plants. This is a plant that has been recently built close by. It's built on the Secchia River, and here what they did is a diversion of the river to convey a huge amount of flow to two turbines. And the turbines are located about 200 meters downstream the diversion, and then after the turbining, the water is given back to the river. And this is where the turbines are located. This is what's called the hydropower plant, and the turbines will be installed, and they are already installed along these two huge cylinders. And here there are some pictures of the channel that brings water from the river to the turbines. It's a closed channel. The reason why they wanted to close it is to minimize the environmental impact. The idea was that everything was undergrounded in order that nothing could be clearly visible from in the landscape. And this is okay, here's a child, but to give you the dimension, an idea of the size, and this is the step between the gravel trap and the turbines. And this is not a sudden step, but it's a steep slope in order to block the sediments. And here, this is the flushing discharge, the bottom discharge. And you see the dimension, the person is about 180 meters, so you get an idea of the dimension of this window. This is taken, again, a picture of the channel. This is the entrance of the channel, and the river is just behind me. Again, the entrance, and these are details of the channel. Again, the entrance again. And these are the two cylinders where the turbines will be located. Okay, this is a panorama picture. And I think I have also some pictures of the plant that is finished. Just let me check. Okay, these are other pictures that I wanted to show you. Just 1 second, because I want to start from the beginning. Okay, this is a barrage that is built on a small river located in the Dolomites with the purpose of producing hydropower. And this is interesting because you can see this is quite small. If you look at the main spillway, the width will be something like 6-8 meters. And first there is a bottom discharge that is this pipe here that is included in the main spillway in order to avoid flushing of sediments that accumulate upstream, because they wanted to make sure that once in a while they were able to flush the accumulated sediments, because they want to keep some reservoir upstream in order to allow for compensation. And then, and this is a distinguishing feature of this plant, they didn't have much space in order to make a lot of facilities on the sides, and therefore they decided to withdraw water through what is called a bottom grid. So the water withdrawal is occurring here. This is a grid, and so you have water flowing over this grid with priority because it's at a lower level, and therefore water is withdrawn through this priority grid. There is no environmental flow weir here because this is an old structure, and the environmental flow is today released after the gravel trap and sand trap, which is here. You have the water that from the grid is transferred to the sand trap here, and it's a unique pool, sand and gravel trap. Keep in mind that in this river there is not much sand. The typical size of sediments is quite large. And then from the trap you have a release of the environmental flow, and through a grid that is located here, you have water that is conveyed downstream with a pipe. This is an interesting, I think it is an interesting plant. And here you see a detail of the grid. And here you see a detail again of the grid and the weir, and here you have an instrument for measuring the water level. And I think this is a wire. I'm not sure whether this wire is meant to monitor the stability of the structure, because maybe that they measure extensions, the length of the wire in order to see if there is differential movement of the structure, or maybe that they use the wire to put some measuring instruments once in a while over the wire in order to measure the water level. And this is a detail of the bottom discharge of the sand trap. And here there is a gate which is maneuvered through an engine that is pushed there. And the engine has maneuvers the gate by rotating this I don't get this. It's like you know, yeah, a staff, yeah, but it's what in Italian is called a vite senza fine. And let me say, let me check.
A screw.
Yeah, a screw, yeah. I thought that I was not. I thought that screw was meant was the word for the screwdriver. No, it's a screw, and it's a screw without end. We say in Italian, which means that it can rotate indefinitely, and therefore by rotating the screw you get the gate up and down. Okay. that's it. And I wanted to check whether I have other pictures of the other plant finished. Let me see. I'm sure I have them, but here it is. No, this is another. I take the opportunity to show you another set of pictures that are interesting. This is a barrage that is built, that has been built over the Secchia River again. It has been built in 1980. Yeah, 1980. So it's about 40 years old. And what I wanted to show you, this is the fish ramp. It is seen from above. If you look on the right part of the picture, there is a small channel. It's the it's the fish ramp placed downstream the environmental flow spillway. And there are interesting pictures because if you look downstream, you see what happened. There is the bedrock emerging, and the bedrock is emerging because the barrage trapped all the sediments upstream. Indeed, they collected upstream the barrage in 10 years about 1 million cubic meters of sediments, which is a huge amount. And downstream, the bedrock emerged, and what happened is that you see a canyon originated. This canyon, it means that you see that there is limestone and the clay at the side of the river. The river eroded the clay for about 7-8 meters deep, and this occurred in about 10 years, not 50 years or more years. In just about 10 years, by blocking the sediments, this canyon originated. And this is a problem. You see the canyon on the right. It's a problem because it undermines the stability of bridges and other infrastructures. And it's really, this was a field trip with the students. Okay, and this is the plant. This is the plant that you have seen before during construction, finished. These are the turbines. These are the turbines, and you see that this is the energy producers. The turbine is located down here. This is a detail of the turbine seen from above. And they are placed in the two big cylinders that I have shown you before. And this is the canal that you have seen before during construction, with the water flowing. And these are, you have seen pictures during construction before. These are the gates that are maneuvered in order to bring water. The big one is the water that is delivered to the turbines. The small one is opened in order to evacuate the excess flow, bring it back to the river. Okay, that's it. Good. Now let me go back to here, because there are a couple of things more that I have to say. And design of site structures. First, main spillway. I talked about erosion downstream, and erosion can be avoided in several different ways. You can avoid erosion by placing big boulders downstream, and this is the solution that is most frequently adopted because it's environmentally friendly, and also it's not very expensive. It is subjected to uncertainty because what is the size of the boulders? This is a big question mark. And the stability of boulders can be increased by connecting boulders with wires, and this is used, or sometimes we try to stabilize the boulders with concrete, because there is, as I said, this big question mark, because we really don't know what happens during a flood, And sometimes we see boulders that are large, like houses that are floated by rivers that normally have no water during summer. Because it is typical of torrents, there is a big difference, several orders of magnitude between mean flow and max flow. And therefore, you know, it's an attractive solution, but the problem is that sometimes we are not very sure that it can resist. Keep in mind that if downstream protection is removed, it means that probably also the infrastructure is removed. Because once that the river starts excavating downstream, the stability is rapidly undermined. Another solution is to build downstream a pool, and this is largely applied. So downstream a structure, you build a pool of water. Of course, the pool can be made by concrete or by natural material like stones. The purpose of creating a pool is that when you have the flow that is landing into a mass of water, of course you have a huge dissipation of energy. It's water itself that protects the riverbed. It's much better to have the flow landing over water rather than the flow landing directly on the stones. And let me check if I have some pictures to show you again. One second.